So let's say we want to bake a pie crust. We can start with a cold stick of butter, and we have a few options as to how we can combine it with the rest of the ingredients. We can either throw it in there whole, or we can use a cheese grater to divide it into much smaller pieces. Now, while we'll definitely get a better pie crust if we use the second option, we haven't done anything to fundamentally change how the butter interacts with the world. That's how the materials we see at the macro scale behave. Size doesn't really matter. This is different at the nanoscale, and it's particularly important for a class of materials called semiconductors, which, as their name suggests, sometimes conduct electricity. Semiconductors need some sort of additional input of energy to become conductors. Most of the time, this comes in the form of light. The light activates the semiconductor and creates two activated charges: a negatively charged electron and the positively charged hole it leaves behind. These can move throughout the material as an electric current. In solar cells, the high energy electron is removed from the material and used to power anything from a light bulb, coming full circle, to an air conditioner. This changes when we take these materials down to the nanoscale though. We've entered what we call the quantum confinement regime. Quantum confined semiconductor nanoparticles, also called quantum dots, force the electron and hole to be together. The smaller the particle, the closer the two charges have to be. Therefore, it takes more energy to separate the two charges. This means that by changing the size of the particle, we're able to change the energy of the light that it takes to activate the material. The same thing happens when the material deactivates. The electron and hole come back together, and they give off light. Smaller particles give off higher energy blue light, whereas larger particles give off lower energy red light. The fact that we can change the color of these materials simply by changing their size makes them unique, interesting, and industrially relevant. The quantum dot market is predicted to hit $32 billion with a B dollars within the next 5 years. In fact, you might already have quantum dots hanging on your wall. They're used in high-end displays, like Samsung's QLED TVs, so you can watch a gorgeously rendered cooking show to find your next pie recipe thanks to quantum mechanics.